and actually by pressing further on like a little point over here, as this was one of the things that was first observed by Newton, these rings patterns will also show up, which are called Newton rings. I'll explain this in the next slide. But for now, as you can see that these fringe patterns are linear, as you can see, as we expected, and they essentially give you a sort of outline of the thickness of the film and how the thickness varies. And eventually, when they start to exceed the coherence length or something for the path length difference, then you lose the interference patterns. So let's talk about Newton's rings, and this is the setup that that we will use in the lab and also to observe these Newton rings. And again, as you can see, this is a great way to test sort of the curvature of a lens. So if you have a very flat surface, which is often called an optical flat, you can obtain flats that are flat to within lambda over 100. So this surface over here is extremely flat, and then you put a lens on top of it, and again you observe in the familiar fashion of the Heidinger fringes. You might have, but here we create the extended source by taking a monochromatic point source like a laser, and then expanding it to fill the beam splitter, and then looking at the pattern back over here. Then the distance, at any distance x out from the center of this optical axis, the thickness, if the thickness of the film is d, x squared is related to r by r squared minus r minus d squared. You can see that by just looking at this geometry over here. This distance is r minus d, and this distance over here is r, the radius of the lens, of that lens surface, and this distance is obviously r minus d due to the height of this film, and then the distance x. So we can immediately calculate x as I just showed you here. Since d is usually much lesser than the radius of curvature, we can expand out that r minus d the whole squared and neglect the terms proportional to r d squared, and you get x squared equals 2rd, and therefore the bright fringes, which would again be given by the Fizeau fringes, 2 times the optical path length thickness, is equal to again m plus half lambda naught for a bright fringe. And when I substitute in for d now, d is going to be x squared, proportional to x squared. So x will then be proportional to square root of r, where r is the radius of curvature of the lens, and of course lambda f. So and again the first bright fringe will occur at m equal to 0, and the dark fringes will occur again right at the center. Then we expect to see a dark fringe if everything is properly aligned and accurate, and there are no dust particles or something sitting there. So this is a dark fringe that you'll see at the center, again just as we expected for the Fizeau fringes, when we at the very edge where the thickness went to 0 due to the phase shifts, you get a dark fringe. We can distinguish the Newton's rings fringes from the Heidinger fringes. Even though they look very similar, you expect to see circular fringes even with Newton's rings, and Heidinger fringes also have the circular fringes. But we can distinguish because the fringe has the lowest order at the center. So as x increases, the changes in the diameter of the fringes get smaller and smaller. The fringes get narrower and closer, as opposed to the Heidinger fringes, where as you went further and further out in the angle, because the pattern has a smaller order of the fringe, the diameter is going to get larger. So this is a way in which one can distinguish the two types of fringe patterns. So this shows you the Newton's rings can occur both in reflected light as well as in the transmitted light. So if I had looked at, instead of looking at the reflection from that previous setup, instead of looking at the reflection, if I had gone the other side and not had a black surface but looked at it on the other side with a detector, then I would have observed fringes. Now obviously this will be the complement, and you'll get a bright fringe at the center, and then you'll have patterns going outward again, where you'll observe the Newton's rings.